Um, so hopefully I'm not going to take the full hour, so we can keep some time for questions, and even better for give everyone a little bit of time back. But I do have a decent amount of material here on my, just kind of like basically the basis for my thesis. And so I'll give a bit of background about the project and LGO thesis, just in case some of you are not familiar with this. But just before we get started, I do so. Era's introduced the topic. So I was working with Amazon, kind of building computer vision solutions to diagnose some of their problems, which I'll get into in a second. I also have two faculty advisors and professors, Boning from UCS and Go Resai from Sloan. So it's again in the spirit of the dual degree. Um, and as I've mentioned earlier, some of it has been approved, some of it is still pending. So there's nothing really confidential, I would say, but just for the sake of it, do not distribute this outside of the Mimo group and all of this. Um, yeah, let me get started then. And I'll actually start with a very quick intro, just in case, on the LGO internships and kind of what I've been doing there, and how does it fit within our degree. So essentially, we all have a 7-month internship that we conduct in the middle of the degree in collaboration with a partner company, in my case, Amazon, and more specifically sponsored by the operations engineering group. And I spent 7 months full time there, kind of working my thesis and solving a real problem, basically. And so, okay, I've mentioned this. And so I'll get started. So the problem I was brought in to solve was uh, pretty simple, at least in its formulation, a little bit harder to solve. But essentially, they have all of those scanners here that you can see on the right. And across all of their fulfillment centers, and as you must surely know, they have hundreds of fulfillment centers. They have those scanners at the very end of the fulfillment process, meaning once you put in your order, it gets packaged and so on, sent on the conveyor belt. And at the end of this process, scanners will read the barcode, the shipping label, and determine in which truck, in which chute, and so on, the product should go. And this is actually surprisingly hard to do because there's so many, a site can see up to 1 million packages a day. There's so many packages of all kind of sizes. It goes at very fast speed, and a lot of things can go wrong basically on those sortation systems. And one of the things that does go wrong very often, is the actual scan from those scanners. And so up to 10 to 20% of the scans cannot find a shipping label on the image. And when this happens, the package ends up in a separate chute, and an associate manually needs to go figure out what's happening and put it in the right chute. So multiply 10, 20% across millions of packages, and you realize that's a lot of manual work. And it is especially hard to solve because every site is very different. There can be multiple types of equipment, different brightness, different conveyor belts, all kind of issues that are very site specific. So it's not like there's a one size fit all solution that we could apply across the entire network, because every site claims there's a very different reason why their no read rate, as we call it, so the scanner no read rate is so high. And essentially their target is kind of up to 5 or between 5 and 2% error, so very far from the 10 to 20% currently that we see. I'll show in a few minutes kind of examples of images and all the reasons that can cause this, but you can see very quickly kind of an example of some of this image. And in this one, actually, the package is not even on the conveyor belt. It is kind of on what we call the bellows, so in between two carriers. So this package, not only does it not scan properly, but if we don't do anything, it'll be stuck there for the rest of the day until like break time. So that's the kind of issue we can see, and that's one of the many reasons we'll attempt to fix with this product. But this is kind of like what we're basing all of our work on. More specifically, the goal of this entire project was to develop an end-to-end production tool. So a tool that we can run across all of our sites and to diagnose the reasons for those no reads. So it's not about fixing them necessarily. Obviously, that's the ultimate end goal, but more specifically, want to diagnose and be able to tell for every site, look, 40% of your no reads are caused by packages that are not positioned properly, and 20% are due to packages that have fallen off the conveyor belt, and 20% are due to packages being damaged, and so you want to kind of be able for each site to tell them, give them a breakdown, and then they can go and act on kind of the specific site reasons that we've identified. So that involves more specifically creating classification models using deep learning on the images. It also involves kind of having an entire pipeline that goes from users inputting images or kind of us extracting from their local machine, all the way to having a website where they can see the results for their site and visualize kind of the results, as well as making sure that it actually works by piloting it across a pool of sites. So I'll cover all of those throughout this. So again, the kind of today I think will be basically a third machine learning, a third kind of like more AWS focus and how can you process all of those things, and then the third on the actual operation side. Again, I'll go through in details all of the elements of this solution, but in short, the tool we developed, as I mentioned earlier, handled everything from uploading the original images from the scanners directly to an Amazon Web Services or AWS server. And so I created the entire pipeline and so on to pre-process, augment, and so on. And we'll get into details, but also generate some additional features. Kind of staying in the spirit of leveraging the AWS resources, I've actually used something called Amazon SageMaker, which is their kind of cloud machine learning platform that you can use to train models and deploy them. There's a lot of really cool stuff you can do with this. So I'll also cover this in a second, but it's a really good way to kind of deploy the production models. And at the end, there's kind of a Tableau equivalent that Amazon owns. It's called QuickSight. Not exactly actually Tableau equivalent because it's, again, cloud-based and you've kind of integrated websites, but similar idea of like using dashboards and so on. So that's kind of like the final dashboards that the user could see online. So that was the end of the end-to-end tool, sorry, and kind of all of that within the 7-month time frame that we had for the project. And by the way, I haven't started getting into details underneath this, but if you have any questions, feel free to interrupt or post in chat or whatever. Really don't mind. Okay. So let's get
maybe one question for me, Felix. How easy was it to easy or hard to do things on SageMaker compared to just doing it from scratch?
So SageMaker, it essentially is mostly based on Jupyter notebooks and kind of very easy, very easy to quickly do some exploration and develop a model and so on. Where it gets harder, though, I felt it didn't have good support for production code, meaning like code that does not reside in the Jupyter notebook. So all of my code in the end was not in the notebook; it was in your regular .py files and so on. But kind of integrating all of this, and I could not have like automated builds and stuff like this that you may want in some of the production code. So I think the short answer to your question is it's very easy to get your first models up and running, but if you want something that's a bit more robust, then this is where it gets trickier. But overall, still a very good tool. And I think most data scientists are typically not interested in production models and any of the things I've mentioned, so they're very happy to develop a model in the SageMaker console and notebook.
Okay, cool. Thank you.
So yeah, let's do first of all a deep dive into the data and kind of what kind of images we had, what issues we're seeing, and how we could process them. So here are a couple of images that we got, that we could get out of those sites. So all of those, and it's really important to say, all of those are no reads. So we only have faulty images, and we're only interested in faulty images. So we're only interested in telling a site out of your faulty images, so again, your no read images, your no reads, what are the reasons for those? So all of the images are no reads, different causes behind them. So this one, you can see there's literally no package, right? Which could be caused by a variety of things, either equipment issues such as bad timing for your camera, or sometimes just the package fail off or something like this, which does happen for some sites. So that's the first type of thing we'll be classifying. Actually trying to understand or quantify all of the images that have no package at all. Another issue that can happen with the scanners is if you have multiple labels on the same image, right? Then you'll get an error essentially. And the scanners are really not smart, unfortunately. They just return an error. They don't even tell you the reason for it. But that's one of the common ones in with some of the lighter packages, like those kind of envelopes that can fly off. And it is obviously good that we've get an error, because the last thing we want is to not realize that there's two packages there and kind of eject both at the same time, and then one of the packages will end up in the wrong city. So this is actually a massive problem in some cases. Whether we see or not two shipping labels, we do want to flag those. So that's another kind of classification we have to work on. Another thing that's also important, they had no visibility on, and that's not per se a reason, but the type of packages, once combined with the reason, is really important. So one of the things that we wanted to do is from an image being able to tell, is it a box? Is it a tote? Those are kind of yellow totes, you can see it here, but kind of bigger and contain a few boxes themselves. We have the envelopes here and kind of the plastic packages. So some sites have very specific issues related to the one of those packages. So it is important for us to be able to tell in the image which one it was. Another ambiguous reason that we'll need to be able to report is the position of a package, which is quite tricky. But essentially, the rule we've used is that if the center of mass, the estimated center of mass of a package, is not on the carrier, right? It can either be on the middle bar between two carriers, which we call kind of overlapping, meaning it's kind of stuck between two carriers and may or may not be on one of the two. It's hard to tell. We don't know how it would be ejected. So that's one issue we want to kind of debug. But another is when between multiple sets of carriers, we have those bellows here, kind of accordion shape. It's hard to see, but we call that bellows. And we want to separate the packages ended up in those bellows here, as opposed to those, because those will be stuck all day, literally until the break time and someone removes them. So those are kind of like a sample of the type of thing that we can identify from an image. There's more that we can do. Some of it that we were looking at tackling, some of it that we kind of put aside, such as the damage on a package, which is really getting more ambiguous and harder to determine from a 2D picture. But there's a lot of other reasons that we could also look into that could cause no reads. And so we had literally millions of images every day, actually, across over 100 sites. So that's a lot of data. We don't need to analyze all of it or use all of it for training, but we had access to it. And that comes with its own challenges. So the images I've mentioned earlier are or the scanners are not very smart, unfortunately. And I talked to the vendors trying to do something, but there's really not much that can be done right now. But essentially, we just get an image, and the scanner tells us couldn't read. Those images are not labeled, right? So if I'm going to build any machine learning model, I need to tackle this. All the images are in grayscale. Color would have been great for some of those packages, but it's not the case. And even the resolution will vary across sites because there are multiple vendors for the scanners and setups and models and so on. And there's also other challenges, which I'm going to spare you, but images sometimes can be easy to extract automatically from the scanners and sometimes not, so it can always change. From a modeling perspective, we'll also see there's challenges coming across the differences between those setups, right? So the brightness, the angle, the zoom, all of those can change, and that makes it much harder to train a model. I'll explain kind of issues that we found out with this. Still, we extracted 2,300 images that I manually labeled for each of the categories that I showed earlier across 10 different sites. and kind of did some cleaning and cropping and so on, but not much. When I say label, again, it's really just applying all of those labels that we see here, not like segmenting anything within an image or anything like that. It's really just overall labels. And another thing, which is quite interesting, I'll talk about it later on, but we actually, even though those are grayscale images, most machine learning models or deep learning models use for computer vision actually use RGB, an RGB format. So we're converting the grayscale images to RGB by replicating the grayscale value from 1 to 255 across each of the 3 channels, which is the usual way of doing it, but we can actually improve this a little bit better, as I'll show later on.
I have a question.
Yep.
Like what is an image in this case? Because I thought like the scanner has multiple head, so is an image one head of a scanner or like?
Yeah. So all of the images we use are the overhead images. Depending
Okay.
on the side, some also do have those side scanners, but it's actually a little bit awkward to work with. And it is in the plan. We've actually talked to vendors to kind of, they're working on getting a single 3D image generated from all the scanners, but until then, we only focus on the top view.
Okay, I see.
Yep, so that's for the data. Very quickly, but I think that's just because that's a good intro to the next slide. But I, as usual, did a lot of data augmentation on this, more than double the size of the data set, applying all kind of transformations, right? Your usual transformations, zoom in, brightness shift, a little bit of shear, vertical flips, and so on. And that's kind of one of the problems that we had is our packages essentially can be rotated by any factor, right? It can be anywhere on the carrier as well. So they're not always perfectly centered. They're not, there's a lot of small variations. And surprisingly, a lot of the algorithms that we use for this and are common for computer vision are actually very bad with small environments like this. And this is actually a really big problem that I've been kind of working on separately. But so we ended up using ResNet. I'll mention it later, which is a very common deep learning models for this. And ResNet, like most models, does very well in its training set, but will behave very oddly to very small changes. And it is kind of counterintuitive. If you've done just a little bit of or seen a little bit CNNs, you're kind of like, everyone has the everyone thinks when they first see it that the architecture of CNN means that if you rotate the image a little bit or translate it by a single pixel, the forecast will be, the prediction will be the same, right? That's kind of it should be an artifact of all of the convolutions we've done and so on. But the reality is very, very different for those models, and they're actually very bad. And I pulled up an example that I looked up yesterday, and this is so this is using Inception v3, but very good model, as good as ResNet. And if you feed this image and you ask it to predict, it'll say it's a banana, 99.5% confidence. So obviously, everything good. If you do a 1 pixel translation, which is not even visible by human, but there should be like a 1 pixel shift essentially here, it actually thinks it's a slug with 98.8% accuracy, or not accuracy, but confidence. And that's just a major issue with those. Typically, I think for ResNet, a single pixel translation is about I think 7 or 8% chance of the prediction switching. So those models, unfortunately, because of all kind of subsampling issues, are extremely bad at this. And using them for a problem like mine, where package can be in any angle, will require a lot more of those transformations to ensure this invariance.
Felix, can I ask you, if you go back to the prior slide?
Yep.
It looks like you I'm actually surprised that you didn't augment the data by more. Is there any reason that you didn't just take, discrete intervals between, say, -15 and +15 and sample all of those?
Yeah, so we did. I did actually generate more images. I ended up using 5,000 because that was a sweet spot of just the accuracy we wanted. And
I see.
but you're right. We can definitely go with more. Those are fairly long models to train. Um,
Mhm.
but it's a good point. You also come to a point where what we realized is that data augmentation helped, but it was always better to have new images. So my time was usually better invested uh, labeling 100 new images from new sites where it is.
I see. Okay.
But yeah, that's a good point. So yeah, we have all of those issues there. And still, we want to tackle it. We want to leverage as much as we can of those models. And so let me now talk about how we can do that in AWS SageMaker. So just a quick overview of how you can work around SageMaker. So you can still do your code locally. At least personally, I like it because locally I have PyCharm and all of this, so I can do a lot of my development locally. But I always push my code to SageMaker where I can run it from a notebook. And a good thing about SageMaker is you can really kind of it'll save on your resources by having different instances allocated to training, to inference, and so on. So in SageMaker, you can have an ephemeral GPU instance just for training, right? So just to give you an idea, I think each GPU instance, the cheapest is about $3 an hour. So it kind of adds up if you were to use this for full-time inference and you have a couple of them. So you can have an ephemeral that you just pay the $3 an hour for GPU using when you're training. But then SageMaker also allows you to perform inference. And I'll give an example later on. But essentially what it means is you can spin up a separate machine where you host all of your models. And this one you can, depending on your needs, obviously, you can have something that's much cheaper, a couple of cents an hour maybe. And that is just kind of running 24/7 the cloud with its own API waiting for you to query it and ask for results from all. And SageMaker just makes that very easy through kind of the interface to have manage all of those resources, and obviously have your S3 bucket and Amazon for all your data. So really just neat way of having all of this. And I had used a lot of AWS in the past, but I was always doing kind of everything on my own EC2 instances, and I felt that there's a lot of waste in the end from having those GPU instances that were not always running, and sometimes you forget to turn them off. And you can also use ephemeral instances, but it's kind of a little bit clumsy, I feel. So that was a really neat way of doing that. And just maybe talking a little bit more about SageMaker. I'm not sponsored by SageMaker, so you feel free not to use it, but I always like to share it because I at least had never used it before. So one thing that is good, as I mentioned, you can optimize resources, very helpful. I also found it very helpful for hyperparameter tuning. You can just let it know what your hyperparameters are, kind of some guidelines around how many tests and so on. I'll actually show what I've done later. But essentially, you can run all of your hyperparameter, and SageMaker will just save everything, and you can always go back into AWS console and say oh, what did I run 3 days ago? It'll tell you okay, you run this combination of hyperparameters. Here was your optimal model based on those hyperparameters, and we've actually saved it for you. So you can always go back, and it just makes it very easy to share with the rest of the team. And now that I'm actually gone, right? I'm no longer at Amazon. Anyone in the team can still go back to what I did a year ago and see what tuning job basically led to my final model. So very easy way to do this, I felt. And also very easy way to deploy models. You literally just load your model on your endpoint, and there's a kind of an API ready to go. So anyone with the proper permission can just query your instance and say I'm interested. This is from their website, so that's not the models I built. But you can say I want the New York model, or in my case, is there a package model? And here's my image. Can you return me the classification? So it's very, very easy to do. and supports multiple models at the same time, which is also very important. So now that I've taken this, there's one last thing that I want to come back to, because I think that's one of the interesting things that's kind of new, actually, from this thesis, is how to leverage the 3 RGB channels. And essentially, I struggle a lot with the idea of replicating my grayscale value 3 times, which I know is the kind of textbook way of leveraging those pre-trained models. I'll use in I'll explain in a few minutes. But I still felt there was a lot of information being lost from replicating this. And what I ended up doing is saying essentially, we have 3 channels. I'll keep the grayscale in the first channel, but the blue and the red channels, I actually want to do something else with them. And what I did is I performed on the blue channel something that we call candy edge. I think next slide will show how it looks like, but essentially identify edges in your picture and just highlights them, right? So on the blue channel, we now had just a 0 or 1 value. That's 0 if there's no edge, 1 if there's 1, which kind of just overemphasizes the edges of the package, which is really important for what we wanted to do. And on the red channel, I actually used, this one is a rule-based approach that would tell the algorithm the difference between the metal bars that we saw earlier and the bellows, which is also very tricky, even for humans. But essentially, you wanted to be able to understand that the double thin metal bars here, and they'll appear in red, are different from the large accordion metal bars here. And so kind of this is something we can identify rule-based, and in an image highlighted it in red. And I'll show you. And it looks like this essentially, where now I've separated them, but in reality both would be combined. But you can see your candy edge like this, and your red like this. And I have a couple of slides in results, but it significantly improved the accuracy there. And so that was a pretty interesting, creative way, let's say, of using your 3 channels. But before talking about this, a final thing that was pretty neat about SageMaker is so for the hyperparameter tuning, yes, you can do your grid search or your random search if you want, but for CNNs, that's just typically not a good option. It's too costly. And you can actually, it now supports Bayesian search or Bayesian optimization for those parameters, where, I mean, the name kind of implies it, but essentially, you can use your previous results as a prior, and then make an educated guess about what next values of hyperparameters you should test. And essentially what it means is you end up testing a lot fewer combinations than a grid search, but you're still smarter than random search, because your next combination of parameters is not purely random. It's still an educated guess. There's still the risk of ending up in a local optima, just as I guess in random search. But ultimately, it does tend to perform much better. There's been a lot of interesting research lately on this. I thought that was really, really interesting that they actually support it within SageMaker. So much faster for CNNs, a much faster way to tune your hyperparameters. So yeah, let's talk about them all a little bit. I kept mentioning ResNet, but didn't actually form or properly introduce it. So just to give a bit of background, I know everyone has very different backgrounds, but we have all of those convolutional neural networks that we use for your typical computer vision classification. There's been a lot of those models out there over the years. And the earlier models struggled with an issue that arises with deeper models. And that issue is around the gradient, and how you can have kind of a vanishing or even exploding gradient depending on the depth of your model. And I guess without getting the details, the challenge there is, for many years until 2015, we couldn't get deep models to work. And in 2015, ResNet came out, won the ImageNet competition for that year, and kind of just through a pretty simple process, I guess, of introducing shortcut connections with between each layer with the identity, it managed to I'm not going to say fully solve, but greatly help kind of this problem and come up with very deep models. So the one we use is 50 layers, but we've actually also trained our model with one, or tested, I guess, with one that was 101 layers. So there's you can go for very deep models this way, and it greatly improve the accuracy versus other previous models. There's been a few other new models since then. Inception is one. There's even Inception, ResNet, and so on. There's not been kind of meaningful improvements over ResNet, but in some cases, for specific applications, some can be a little bit better. And so we tried a few, but ultimately, ResNet is the one that is kind of the most supported by SageMaker, and kind of have its own container and so on. So that's one we ended up going for. But the good thing about all of those models is they were trained on the ImageNet datasets I mentioned earlier. I think in 2015, there was about 10 million images. And what it means is the models already got really good at extracting features from those 10 million images that are very different from packages. We're talking but it's still, those models learn to extract features. And what we can do is through a process called transfer learning, is keep all of those weights and only retrain the final kind of fully connected layers, and retrain them with packages instead of pictures of dogs and cats. All of the feature extraction layers are still the same. It's really just the final layers that we're retraining, which you can then do in a reasonable time, as opposed to retraining the whole model, which obviously with 10 million images would be a problem. With 5,000 images is better, but it still can take a while. And I have some results later when I show the difference, but actually the model definitely outperformed, so the model through transfer learning outperformed the model that was purely trained on those 5,000 images. So there is a real improvement to be made from leveraging this big feature extraction process, even for a problem that is seemingly very different, right? Classifying packages doesn't feel the same as identifying dogs and cats.
How many layers did you end up retraining, and what was the structure of those layers, and how did you decide what the optimum was?
So I just retrained the last 3, which is there has been attempts to retrain more than those, like basically it's essentially just a fully connected layer that matters, and kind of what we do at the end of softmax. There's been attempts to retrain more than this, but I haven't seen anything convincing on it really helping. And locally, so on my laptop, I tried to also retrain more than 3 layers, and it really wasn't helping in any way. And actually, SageMaker now only supports retraining those last 3 layers. So that's just what I went to, and it's really, I have it there. It's just a global pooling, the fully connected layer, the final softmax at the end.
Thank you.
So now we can talk a little bit about results and what we're getting out of this. So actually, before I talk about this, just kind of setting expectation, I mentioned we're talking about what we want to tell a site is something at the aggregate level, right? We want to tell them 40% of your images have X issue, 20% of Y issue. It's not about making real-time decisions. So what matters the most for us is really the overall accuracy, and especially at the aggregated level. But good individual accuracy obviously leads to good aggregate accuracy. So we're optimizing for individual accuracy in the model itself. So looking at this, the first chart here, we can see so for the 4 main models I've described here, and the first column tells us the accuracy when we retrain, so we don't use transfer learning. So pretty good, right? This one, that's the ambiguous one about the position, which is definitely harder to identify. But still, we got 87% accuracy and so on. However, using transfer learning, we did significantly better across all of those models. So if you look at, so the blue is the model we ended up selecting. For the MT carrier, which is a pretty simple problem, you expect to do well there. Using transfer learning, we got 100% accuracy. This is so this is actually on the validation set. So we did very well across all of those, even this one. And this is also where we see for those models that were kind of harder, especially this one, right? Adding the highlighting bellows in red really helped from 89 to 94%. So this is where we see a kind of a meaningful improvement from this pre-processing in the red channel. But again, more importantly, I think what we're interested in is the aggregate level. So in the final test set, the worst error we had was 1.8%. Meaning, again, if we have our or in this case, 3 classes actually. If we have our 3 classes, the biggest error that we see is 1.8%. So if you tell a site 22% of your packages are missing, they don't really care if it's actually 23.8. Like all they want is a directionally correct issue identification, and 1.8% was way under our initial goals. I think we're more in the 5% range when we were working on this. So again, when we could tell a site all of the main reasons, they were more than happy with this kind of aggregated error, and especially kind of, as I said, across this is across many sites. Some could have extremely low errors, but others were a little bit tricky of kind of going towards that 1.8%. But yeah, overall, again, highlights the importance of transfer learning and those pre-processing techniques there.
Can I ask a quick question?
Yep.
What's the difference between the test accuracy and the test error?
Yeah, those two here.
Yeah.
Yeah. So this is at the individual image level, and so like in the worst case, we got 89% accuracy here, but of the 10%, a lot of them were essentially canceling each other when you aggregate it. So that's why, yeah, that's why we get there.
That makes sense. Thanks.
We can, sorry, this is a little bit blurry, but we can see or look at confusion matrices. Won't go too much in details, but there's still some classes that can be ambiguous. I think the biggest one was, or the biggest ambiguity is around kind of the when a package is actually on the bellows. In a lot of cases, we think it is overlapping, or we're still not sure if it's predicted. So there's still some ambiguity here, although when a package is centered, we identify this properly. And there's also interesting challenges here where I think it is this one, yeah, here. So kind of those brown envelopes and the boxes can look very similar without, in a grayscale image, we also seeing some error there. But overall, again, not the end of the world given our initial goals. How am I doing time? Okay. Maybe a few last things on the actual tool. So we could actually deploy it and test it. So I created a pretty simple website where anyone can upload their images. We initially wanted the tool to automatically load images from sites, but due to unfortunate VPN issues, we could not. Someone from sites kind of need to manually upload the images. This is something the team is working on right now, so I don't know if they have fixed it already. But at the point where I left, this kind of was used more as a debugging tool, still used by all sites, but essentially it's at the end of the day, if your no-read rate is high, you upload your images, which is very easy to do, to the tool, and within a matter of minutes, you get all of your classification there on a quick site, redacted quick site in this case, site. And we tested this across multiple sites, but one that we kind of ran a larger case study for 2 weeks, essentially. We ran this daily and helped the site operations identify all kind of issues, actually. So we identified a lot of issues with their yellow toads, and they traced it down to a broken belt where the yellow toads are being inducted, so they could fix this. They also realized that they had an issue with some of their lighter packages that keep flying off. So this really led to basically a lot of good insights there, managed within a short time frame, a couple of days or weeks, and depending on the site, to reduce the number of no reads significantly, and also identify kind of broader issues with, for instance, some of their envelopes under a certain weight, I think it was 200 grams or so, just tend to fly, given the speed of those conveyor belts. And it's something we've kind of brought up because we see all of those lighter envelopes kind of all over the place. So really helped support a lot of the site operations, which the issue was a lot of them had an idea of what was going on, but without actually number backing up their claims, no one would truly believe them, or it'd be hard for them to claim that there was specific issues. And now a lot of them could be empowered with this. So yeah, in the end, we reached our goal of at the aggregate level, kind of 98% accuracy. Our goal was more than 95% originally. We actually deployed this. So we piloted it across 10 sites, but then at the end, fully deployed it across 100 sites and kind of demoed it across all of them. So I still get pretty frequent emails about it, so I know it's being used. I'm hoping as many of the 100 sites in scope are using it as possible, but I know there's a lot of interest there. And a lot of interest too in expanding it. You've probably identified yourselves way that we can improve this. There's a lot of models that we did not produce just by lack of time or data, such as whether a package is damaged or so on. So there's a lot of ways we can expand it and also kind of have it run or be automatically kicked off whenever a site has a high no read rate, rather than having someone manually kick off when the read rate is high. So there's a lot of things that we can do, and there's actually the operations engineering team following this project decided to launch their first computer vision team. So I think they're starting to staff it right now, and hopefully we'll tackle more of those projects in the future, because there's a lot of applications in fulfillment centers. So yeah, that's all I have. I think we have a tiny bit of time for questions, but I know there was quite a lot for 45 minutes.